Hello everyone. We have here one of the most famous problems in physics. We have a box and an inclined plane. You'll see this if you take another physics class in college. You'll see this problem. If you decide to go to pursue a career in physics, you'll see this problem in physics. I still look at this problem as I am completing my master's degree, so yeah, let's get right to it. A block is at rest on the incline shown in the figure. The coefficients of static and kinetic friction are mu sub s 0.78 and mu sub k 0.66 respectively. The acceleration of gravity is 9.8 meters per second squared. A. What is the frictional force acting on the 17 kilogram mass? And B. What is the acceleration of the block down the incline if the angle of the incline is 40 degrees? Assume that the block will move at an inclination of 40 degrees. You may recognize this problem from your homework, and it had three parts. I skipped over the second part. That one asked for you to find the maximum angle at which the block would remain static, like it would move. And the answer, at least using these numbers, it was something below 40, which means that at 40 degrees, it will move. Okay, so let's start with highlighting the information which we know is important. And I'm going to pick blue for question A and then green for question B. So we have, well, I guess the mass of the block will be the same for both. So for question A, we have a frictional force acting on the 17 kilogram mass. So it's based on this one. And this setup, I guess, with 34 degrees is the angle. The system is not moving, is static, which means we need static friction. So we'll use this one for question A. And that's pretty much it, right? Then I'll use green for B. So now we have kinetic friction because now it's going to be sliding down the incline. I'll use yellow to highlight the information that is going to help us for both questions. We have acceleration of gravity, 9.8 meters per second squared. And then we have a 17 kilogram mass. Oh, also, green would be the 40 degrees. And I'm just going to, well, I guess I'll highlight it too. The 34 degrees is going to help us solve or find question, yeah, I guess not find, but answer question A. Let's write down the given. I'm going to use purple. Let's see what we have. We were given the coefficient of friction, static, 0.78 unitless. Then we have kinetic friction coefficient 0.66, and then we have lowercase g 9.8 meters per second squared. We have a mass. It's only one mass, so I don't need to have mass 1, mass 2. It's just one. 17 kilograms. And then I'll have theta 1, or let's call it theta A, just to show that that's the angle we're going to use for question A. So theta A. Man, that's very ugly, huh? So let's try that again. Let's try that again. Theta A, I guess. That's going to be 34 degrees. Then theta B, that's going to be 40 degrees. So this means question A, this is the angle for question A, and this is the angle for question B. And we have to find both the frictional force. Now question A is when the block's not moving, so we have to find static friction force, F sub s, and then we have to find the acceleration of the block, for question B. Okay. Next step, you guys know, draw your free body diagram. I'm going to trace the shape of the block. There you go. And I'm going to make it a little bit bigger so it's easier for me to draw forces and all the things which I'm supposed to do here with the free body diagram. I think the center of mass is somewhere there. Let's start with the weight of the object. We know that the weight is present because we have the force of gravity acting on it. Okay. There you go. Not bad, not bad. We'll label this as mg. That's the weight of the block. And then we have a surface, right? The inclined plane is a surface, therefore we should have a normal force perpendicular to it, like this. Normal, not natural. I still don't know why students like to say natural. I really don't. There you go. And that'll be normal force, funny n. And naturally, if this were frictionless, if the inclined plane were frictionless, the block will just slide down the incline. Therefore, the natural direction of motion would be down the incline because of the weight of the object. So that means friction is up the incline, like this. So you have static friction up the incline. There you go. Friction static. Next, we would need to sum the forces. We have a problem though. They're not pointing at the same directions. In fact, this is weird, right? The only one like along the y-axis you could say is the weight. And we want to make sure we have most of our forces aligned with the coordinate system. So now what we're going to do is, well, we're going to change our coordinate system, because why not? Because we can, because that's what we do in physics. I'm going to move this, don't worry. I need to make sure that my directions are aligned and parallel. There you go. Now I'm going to move. So that one. There you go. More or less, I'll try to center it. There you go. That's more or less what I wanted to have. Let's see if I can just get the... I'm going to copy. Then I'll get rid of this stuff. So my drawing is clean. There you go. And we'll label a coordinate axis. This will be the y, and this will be x. Let's make this smaller. There you go. So now we have the normal force moving along or acting along the y direction, and we have this static friction force along the x direction. That means the only force which is kind of in two different directions at the same time is the weight. That means we have to use trigonometry to find the components, because we have a component of the weight which is acting along the y-axis like this, which is actually in a way kind of fighting against or acting against the normal force. Likewise, we have a component of the weight which is along the x-axis acting against the static friction. Okay? And we'll deal with that. No, let's add them now. Let's just add the components of the force. So as we said, we have a component of the of the weight acting along the y direction. Should be equal and opposite to the normal force. This one I'm going to call mgy. That's the component of the weight acting along the y direction. Now let's draw the component. Don't forget they have to equal and opposite because the system's not moving. This is the component of the weight acting along the x direction. This one I'll call mgx. Now we can sum the forces. Let me fix that vector. There you go, a little better. Okay, let's sum the forces. The summation of the forces acting along the y will be, in this case, we have no motion of the block like this. It's not jumping up and down like that. So we can make normal positive, mgy negative, or you can make this one positive, this one negative, doesn't really matter. We have no motion there. So I'll make normal positive. So normal minus mgy is equal to 0. We have no acceleration in that direction. And then we have the summation of the forces along the x. In this case, the natural direction motion would be down the incline. That means mgx is positive. Force of static friction is negative. Mgx minus force of static friction is equal to 0 because we have no acceleration there. Okay. We're trying to find, for question A, the force of static friction acting on the block, which means this one. So I'll take this part, write it as a separate equation, and then solve for the static friction force. Let's use, I said I was going to use blue for that one. I'm going to use blue. So we have mgx minus force of static friction is equal to 0. I'm going to move static friction to the right, which is the same thing as adding force of static friction to both sides of my equation. So now I have that mgx is equal to force of static friction. Now I need to know what mgx is, and I can do that because I know the mass of the block and I know acceleration due to gravity, and I also know I need to use trigonometry, right? I got to use trig. So what I'll do is I'll redraw my forces. I'm just going to copy this thing, well, these three forces, and then use trig to solve for mgx. Okay. The best thing would be for me to move this vector here, right? And then I'm going to relabel my diagram. So this is mg, this is mgy, and this is mgx. And I'm looking for mgx. In this case, now we need to identify theta, because I'm pretty sure you're able to identify the right triangle we have here. And this right triangle is based on the incline. Okay? So what I tell my students is try to picture this triangle in the same way as you're picturing this incline plane. And if you think about it, this is the, I guess, this part of the incline. And the height of the triangle, in a way, right? This leg, this height, matches this one. And the bottom, this part, matches this. So our right angle is here. The right angle for this one is over here. I have it here. That means theta A. If I use blue, would it make contrast? Probably not, so I'm going to use black. So this would be theta A, right? That means theta A is here. I'm just going to say theta. But this is where my angle is. Well, I guess theta A. There you go. So now, with this information, well, mgx is the opposite side. I know how to find the weight because I know the mass and the acceleration due to gravity. That means I have hypotenuse, I have opposite. Using SOHCAHTOA, well, that I can use sine. So let's use sine. Sine of theta A is equal to the opposite. In this case, mgx is the opposite. mgx divided by mg, because that's the hypotenuse. I solve for mgx. I just multiplied mg on both sides, and I'll get that mgx is equal to mg sine theta A. Okay. And just for fun, I'm going to find mgy, just in case I need it. I don't know if I'm going to need it, to be honest with you, so I'll just purple over here and say, I'm going to find mgy in the same way. Mgy is adjacent to the angle. That means I can use the cosine. So the cosine of theta A is equal to mgy divided by mg. I solve for mgy. Again, I don't know if I'm going to need it or not, but it's just nice to have it in case I need it. mg cosine theta A. So now let's find what the frictional force is. So I know that the force of friction, static, is equal to mgx, which is equal to mg sine theta A. Now we just plug in our numbers. Force of static friction equals the mass is 17 kilograms. Let's try that again. 17 kilograms times 9.8 meters per second squared times the sine of 34 degrees. There you go. Let's go to decimals. So we have 17 times 9.8 times the sine of 34 degrees. And there's our force. Make sure you have it on degrees, not radians, degrees. Okay, so 93.161, let's say 162, right? We're going to round to the nearest thousandth. So 93.162 newtons. That's our frictional force. Frictional force is equal to 93.162 newtons. Let's box it. There's our answer for question A. I just decided I'll record the other question in a separate video. That way you guys don't have to watch like 30 minutes of me talking and doing physics. All right, see you in the next one.